Okay, continuing, we were talking about the basic Fourier heat transfer equation. I think we were talking about the U is the overall heat transfer coefficient. R are the individual thermal resistances, tube side and shell side. A0, that is the outside surface area of the tube to which everything has been corrected to. LMTD, that's the log mean temperature difference. That stands for the greater temperature difference minus the lesser temperature difference. I probably should have a better sketch of that. I didn't include that, but basically when this term is evaluated, that is the effective temperature difference from the inlet to the outlet that the two process streams see, and what is the driving force to promote the heat transfer between them. Again, the greater temperature difference would be, T2 would be the shell side outlet, T1 is the shell side inlet, or conversely you can have the shell side inlet or the tube side outlet. Depending on how that falls out, that gives you the greater and lesser temperature differences. The lesser temperature difference, okay, anyway, we've already covered that. The correction factor, if it's pure counterflow, there's no correction factor. If it's a multi-pass exchanger, which we'll cover in a little bit here, which shows how that's determined, there's a table that's in your handout showing that. The lesser temperature difference you could also consider to be the approach temperature, which somebody asked at the last meeting. That basically indicates how close you can bring the two streams together and have effective heat transfer. For shell and tube exchangers, that is typically on the order of 10 degrees or maybe a little bit less. The plate and frame exchangers can get down to approximately anywhere from 5 degrees or a little bit less. Air-cooled heat exchangers, your process stream can approach the air temperature, the inlet air temperature by about 20 degrees. So if you want to do better than that, it means you're going to need more surface area just due to the ability to transfer the heat with that temperature driving force. We'll cover that in a little bit here. This shows you a curve of log mean temperature difference. This basically is what I've shown on the previous slide. We're defining log mean temperature difference. This is basically just a table lookup. If you know what your greater and lesser temperature differences are, it will tell you what the LMTD is. Here's a curve of correction factor. There are two other parameters that you evaluate. They are, I'll get my glasses on, the P and R. If you were to look that up on this curve, it would show you this is the correction factor down here. You never want to be less. Ideally, you're 80% or greater on the correction factor. As you get down to 70%, the ability of the exchanger to perform correctly is questionable. So anywhere from 80 to 100% is basically the desired correction factor for a stream. There are other combinations here. You can have a 4-path tube side. That will have a different correction factor. So you need to be aware of that when you're looking at the different designs. HCRI program will basically account for that for you. It will give you a corrected LMTD, and it will also give you warnings if you're in the marginal range. If you can read that, it's also in your table. I believe I handed that out. No, I didn't put that in there. I apologize. This shows you the typical heat transfer coefficients that you might expect for different fluids. Here you have for heavy oils, you're on the order of 15 to 25. The higher the duty and the basically what that means is you have a poor fluid for heat transfer. It means you're going to require more surface area to perform that duty. And when I say duty, I mean BTUs per hour, how much heat you can exchange between streams. I will be putting this all on a folder which you can access and hopefully will be more readable. If you would like to have that as a handout, let me know and I'll be glad to get you an extra copy or add you a supplemental copy. Let's see, this talks about tube vibration, which we touched on briefly. Tube vibration is more susceptible to the stability of the tube in a stream, so the tube diameter, the unsupported span, tube pitch, and entrance and exit areas, these all lead to issues that you need to address to make sure that the unit is not subject to vibration. Again, HTRI program will give you directions on what might be recommended to assure that you do not have a problem.
What were the units on
BTU hour per square foot per degree Fahrenheit. Pardon me, on Q, BTU per hour. On the heat transfer rate itself, the U value, that would be BTU per hour per square foot per degree Fahrenheit.
Is mass flow not coming?
That does in a conservation of energy equation where you would have Q is equal to mCp delta T. Now when you do your heat balance, your tube side and shell side flows all have to balance out on continuity of mass flow and continuity of energy balance. So Q equals mCp delta T has to balance across between shell side and tube side streams and on your heat transfer, your overall heat transfer coefficient or heat transfer equation. So all three Q values have to balance. That's a good question. I probably should have added that in there as a supplemental energy balance. Make sure that's in there for the next presentation. Here's a brief touching on fouling. We have precipitation fouling where particulate will drop out. We don't get too much into crystallization, although that is it's a very interesting phenomena. I know we will have exchangers in a crystallization system where we will cool down a stream which you're trying to grow crystals. They could also form on the tubes, which could be a problem. We have particulate fouling, sedimentation. We might have sand or other things that are entrained in the stream which will drop out and coat out the tube. Chemical reaction fouling, another issue. Corrosion fouling for iron oxides, we might have that in sulfur units where we might be forming iron sulfite, which could potentially coat out the tubes along with molten sulfur. And again, there's biological fouling, which we would typically see in seawater type exchangers or anything that is used a utility cooling water loop that could have organics forming. Again, this is addressed in your handout. Let's go into some more interesting stuff here, hopefully. This is an example of what happens as a process stream flows through the shell side of an exchanger. It's also an eye check too. We tried to clarify the streams. The A stream is the principal stream for heat transfer. We also have other streams, leakage streams, which can cause, let's say, reduced performance or not as good a performance as one would desire. Depending on the, generally for excising an exchanger, we would like to have the window velocity through the baffle about equal to the crossflow velocity. If you have a very high window velocity and a low crossflow velocity through the bundle, you might enhance leakage streams and not have the optimum A stream. We'll have an animation a little bit later on which will kind of clarify that. So that's for general information. This is the animation, which is by ABB Lummus. It's actually to promote their spiral baffles, but it also shows what happens in a shell and tube, conventional shell and tube exchanger with the normal baffles that are perpendicular to the flow stream. Let's jump to that.
ABB Lummus Heat Transfer is a wholly owned subsidiary of ABB, Asia Brown Boveri. The services range from design engineering to full-scope lump-sum turnkey projects, offering fire heaters, plate-type exchangers, and advanced shell and tube exchangers. ABB Lummus Heat Transfer has designed and supplied more than 20,000 shell and tube heat exchangers over the last 60 years. It wasn't until recently that segmental baffles of shell and tube designs were considered to be the only solution to provide tube support and to improve the shell side flow. However, the stream follows a zigzag path through the shell. To create a more continuous flow through the shell, a helical stream is the most logical answer. To facilitate this flow, the helical baffle system has been developed. This unique design does not only improve the heat transfer, it also minimizes fouling and reduces the pressure drop, and can even reduce the total plant investment costs. Not surprisingly, it was awarded with the name Heat Exchanger. By obstructing the flow with segmental baffles, a high fouling tendency occurs in the dead zones behind the baffles. Depending on the fluid, this shortens the run length significantly. The heat exchanger has no dead zones because of the smooth guidance of the flow, so the fouling is minimized and a long run length can be expected. Every shell and tube arrangement has a pressure drop, a great deal caused by the baffle arrangement. Compared to the conventional systems, the smooth guidance of the flow in the heat exchanger can improve the shell side pressure drop up to 50%. Where with segmental baffles the shell side fluid has zones with various speeds causing inefficient heat transfer, the heat exchanger has an equal flow through almost the entire shell, leaving no space unused for heat transfer and therefore having outstanding heat transfer rates. The heat exchanger is extremely suitable to replace segmental baffled bundles in existing shell and tube arrangements. One simply pulls the conventional tube bundles out and inserts helical baffled bundles with all the helical advantages, and this increases the capacity with up to 20%. Another option is to replace conventional trains with a lower number of heat exchangers, maintaining the same capacity while saving plot space and reducing costs. In new plant designs, the heel exchanger can even affect the total arrangement of the exchanger trains and the auxiliary equipment, which will have considerable positive impact on the investments. Helix is a changer. It's the turning point. It's more heat transfer. It's less fouling. It's less pressure drop for less money. Helix is a changer. It is the Helix changer.
Let's see, with my... Yeah, there we go. That's right. Thank you. That's kind of an example. I mean, obviously that was a promotion to promote the spiral baffles, but it also shows you how the conventional units work. We have not tried these units. It's ABB is a very well-known company, so I'm sure that if we have an opportunity, we'd certainly like to give them a try. It looks as though it would be have a great deal of benefit over the conventional units, but so far we haven't had a client that is considering that. Probably if we do any revamps on equipment, this design would be one to definitely consider. This is an example now of hairpin type heat exchangers. Again, these are not a TEMA item, but you'll get an idea of what they are. They're fairly they're small units. You can probably get up to about a 20-inch shell diameter, different tube lengths. One of the main issues of these units are these tube side closure here and the shell side right here. Currently, we've experienced difficulties satisfying external piping loads because of the mechanical design of these units. They're very good. There are Brown Fin Tube manufactures them. RW Holland manufactures them. We have had issues with both suppliers, though, that the nozzle loads from our external piping coming into these units has needed to be looked at very closely because of the limitations of these closures. To pull a bundle on these units, this is a continuous hairpin through the shell here. So you have a pure counterflow design, which is very beneficial if you have, let's say, cross exchange in like TEG gas dehydration units, where you have a rich lean exchange of the TEG. Without a pure counterflow, you would probably have a temperature cross problem. With these, you do not have that. In order to pull a bundle, you take this cover off. You open up this cover here. There's a split ring in there, which then allows you to extract the bundle out of the shell toward this head direction. These units can be stacked as shown here. They can be obtained in multiple alloys and in high pressure designs. So they're a good alternate when you're looking at a relatively small exchanger. There we go. This shows you on configurations that you can get. Unfortunately, scanning these in and having it fit the slide leaves a little bit to be desired, so I apologize. All you can do is get an idea of what's available. If you'd like more details, please stop by and we'll show you a catalog of what is available and give you a better understanding of the type of equipment. Here's an example of an all stainless steel hairpin exchanger. This is actually built for a TEG gas dehydration package that was designed on a component by component basis rather than having the TEG supplier include these as part of his package. If any structural people are here, this one saddle is fixed, it's welded to the shell. A back saddle is sliding, so it can be slid to accommodate just about any foundation that you'd like. Air-cooled heat exchangers. This kind of will give you a background. This was provided by Hudson Products. This is an endorsement of Hudson Products, although I will have to say that they provided most of the exchangers up on the North Slope. Gives you some examples of the various industries that they support. So I'll show you the different types of exchangers they have. There's a forced draft unit where the fan is located below the process bundle, which is shown here. Let me just use the process bundle here. You have your fan assembly below the bundle. The other option is a fan with a spacing between the tubes to allow a shaft to go through up to the top of the bundle, and then the fan is on the top, and it basically pulls the air up from the bottom through the fan. There's an additional discussion as to why that is a preferred design for applications where you have a large number of multiple bays. Just for information, these can be mounted on the pipe rack at grade. They can be mounted on top of a module, which is typically done for North Slope equipment items, mainly to minimize plot space and to maximize the shipping if you're going to do a sea lift of a full module. There are special applications for North Slope coolers, which we'll cover in just a little bit. Basically, the principle of an air-cooled exchanger is to pull in ambient air and blow it across a finned coil and pick up heat and reject that warm air to the ambient. Obviously, the performance of the cooler is driven by what your ambient air temperature. The higher the temperature, the lower your driving force between the process fluid and the air, so your available heat transfer is restricted. For general information, for like a 1-inch tube, the area ratio between the fin tube and the bare tube is about 20 to 22 in terms of whatever units you want to work in. Here's an example of the air distribution for a forced draft unit. You can see the air is coming in the bottom, flowing through the bundle, and then it's discharged out the top. For induced draft, it's pulled in the bottom, and you have a higher exit velocity out of an induced draft unit, which has benefits for multiple units that are side by side. This kind of indicates in this case, the fans are susceptible to water or rain impingement, which sometimes can cause erosion. Another issue is hot air recirculation. On the forced draft units, if you again have multiple bays side by side and you have a prevailing wind, if the exit velocity is not adequate, you can basically pull the warm air around, which is a major impact on your available heat transfer. As shown here, the heat transfer is enhanced, or impact of air is minimized for hot air recirculation. This shows you a typical induced draft cooler, and this shows you multiple bays. Actually, this is the El Segundo refinery for Chevron. Here's another example of 3 fan cell units. This is, I believe they have this at a facility up in near Mammoth Mountain for power generation. This is called a bundle. This is actually a tube bundle where you have a plug header. We'll cover that in more detail in the next slide. This shows you the types of headers that are available. You can either have a full cover plate, you can have a plug header, or you can have a pipe header for high pressure designs. Typically this is what we would use in our industry. These are more applicable to utility coolers where you have cooling water or another type of process fluid in here where you might want to take the cover off to clean the tubes. It's much more labor intensive if you have to pull the plugs on this unit. You have to unplug each one and then either hydrojet or rod out the tubes. Shows you an example of a split header. In case of condensing service where you might have a high temperature drop on your first pass flowing through the bundle. I guess I should use the pointer here. So if we're flowing in the top here and we have a high temperature drop in this header, and then we flow into the next header, since the tubes would be the thermal expansion on the top tubes would be much greater than on the bottom tubes, this allows for the header to grow. So what happens if you restrict it, you're basically forcing the top tubes to deform so that they can account for the thermal expansion between adjacent tubes, between different tube rows. To access a tube, basically, in terms of fabrication, final tube rolling, everything is done through this plug hole here. This would be the plug sheet. On an adjacent sheet is the tube sheet, which we'll see in the next slide. The plug sheet would be over here. So what you have to do is you have to work through the plug sheet to roll the tubes, or to weld them in place with a seal weld, seal weld or strength weld, like is shown here. Shows you an example of the various types of pressures and for selecting the type of cover or tube sheet that you would want to deal with. Plug sheets have gone up to 5,000 psi. Usually on these designs you would also have an internal seal weld to ensure a good mechanical joint between the tube and the header. Fin types, this would be an L-foot wrap-on. It is susceptible to corrosion. It's also susceptible to disbonding. If you lose the bond between the fin and the tube, then your heat transfer rate will drop off significantly. This is for a reasonably low temperature application where your process or your tube temperature is less than 200 degrees. At elevated temperatures, you would probably want to go with either an embedded type fin or an extruded fin. The embedded fin, they'll actually cut a groove in the tube and pinch it back down once the tube fin is inserted into the groove. The extruded fin is a little bit more elegant. That is basically you put a larger wall aluminum tube over the process tube. This could be either stainless, carbon steel, whatever you want, and then you take the aluminum and you mechanically upset it so that you have an integral finned tube over the process heat transfer tube. This also has about a 20 to 22 area ratio between the bare area of the tube and the finned area. Shows you other examples. This is a serrated fin, extruded serrated. This is used when you have severe heat transfer performance. It is not a preferred fin because you have a much higher airside pressure drop, but for critical service where you have limited real estate and you have to make the unit work, this would be an option. Sure.
What's the price difference between, the different types of fins?
The L-foot wrap-on is the least expensive. Actually, the biggest driver is the base tube material. But between a wrap-on and a